Let's welcome the next speaker, Alexander Kilpatrick, from Nagoya University of Commerce and Business, Japan. The title is Machine Learning versus Linear Regression, a case study on gender sound symbolism in Japanese given names. Professor Alexander Kilpatrick is an associate professor at Nagoya University of Commerce and Business, Japan. He specializes in psycholinguistics, computational linguistics, iconicity as a second language, and application of machine learning to uncover complex patterns in linguistic data, thereby enriching our comprehension of language acquisition, processing, and cognitive mechanisms. Now let's welcome Professor Alexander Kilpatrick.
Good day. My name's Alex Kilpatrick, and I'm recording this in case I can't attend the conference. Today we're talking about machine learning versus linear regression, and kind of looking at how you might apply machine learning algorithms as a alternative way of statistical hypothesis testing, or even just exploring the data related to names. This is Japanese given names. It's kind of an interesting case study where Japanese names, if you use traditional statistical hypothesis tests, they do not seem to behave the same way that names in other languages behave in terms of how gender is expressed sound symbolically. However, the machine learning algorithms give us a more clear picture of what's going on. So let's take a look at this kind of interesting case study. First of all, if you are interested in learning how to create the algorithms that I'll be talking about today, I have a tutorial on InvisionBox, or you might find my YouTube channel, where you'll be able to take a look at some of the methods that I apply to looking at linguistic data using artificial intelligence. Before we start talking about gender in this study, I might just move the image of my face. There we go. We're talking about, in this study, we're looking at the gender, how gender is expressed in names. Obviously, gender in today's society, it's kind of this fluid concept. It's constantly changing and evolving. So while we are talking about kind of gender, male, female classifications is what the AI algorithms are doing. If you are working in this space in the future, you might consider a more nuanced view of gender, kind of moving beyond that binary gender association. But just so that you're aware, in this study, the AI algorithms treat gender as a binary classification, which is perhaps not necessarily the reality of the world today. Okay, so for those of you who are familiar with sound symbolism, we know that there are a number of kind of concepts that are expressed through language, through the sounds that make up words. These relationships are stochastic, not prescriptive. So in other words, we can view them through a statistical analysis, but they don't apply to all examples. So this is a fairly common example known as the Bouba-Kiki effect, where we find words that are associated with kind of rounded images, or we make those words typically with lip sounds or with vowels that are round as well. So booba, that's kind of the more of a rounder image, sound symbolically, versus something like kiki, which is more spiky or sharp. Originally, this was known as the Takete Maluma effect, although it's better known now today as the Boba-Kiki effect or the Kiki-Boba effect. There's also the Mill-Mel effect. This is named after by Sapir. Mill and Mel, really what we're talking about here is the medial vowel, where that high front vowel, is associated with small things, and that low back vowel is associated with big things. So what we find in languages across the world is that typically if an object is smaller than, if the referent is smaller than the name for the referent is typically will have like a smaller vowel, a smaller sounding vowel in it. If the referent is larger, then typically it has a larger sounding vowel. Now, if we think about these sounds in our mouths, that high front vowel, my oral cavity is being created smaller. I'm creating a smaller oral chamber in order to pass that sound through. Whereas I'm creating a larger resonance chamber for that larger kind of sounding sound. So the Mill-Mal effect, we find this in many of the world's languages. Our high front vowels denote smallness. Our low back vowels, such as and or, these are associated with the imagery of largeness. But again, these are stochastic relationships. So the example big and small, that's the opposite of what we find, right? So we need to know that these are prescriptive rules. Sorry, these are not prescriptive rules. These are stochastic rules. And we only really observe them when we're looking at things through a statistical analysis. Now, the sound symbolism of gender seems to fall in line with the Mill-Mal effect. Um, so those vowels that are associated with smallness, those are typically associated with femininity, while those associated with largeness, those ones that we create with a larger oral aperture, those are associated with masculinity. Also, femininity seems to be linked to sonority, so sonorant consonants like w, l, and your nasal consonants are typically feminine, while masculinity is linked to obstruent consonants, so a reduced airflow, our stops, our plosives. Um, Bilabials seem to be associated with femininity, but we need a little bit more research on that. And our prototypical names here are Jack and Lily. Jack with that vowel and two non-sonorous consonants compared to Lily with two high front vowels and two sonorous consonants and fairly prototypical in terms of the relationships that we're looking at. Of course, right now you're probably thinking up several examples that fly in the face of this rule, but again, these are stochastic relationships. We view them through the lens of a statistical analysis. Um, Kumagai and Kawahara kind of started doing something interesting with Pokemon, and they were looking at Pokemon names and how kind of the interesting the interesting aspects of Pokemon, how those are reflected in the names of Pokemon. So here we have Groudon and Spritzy. Obviously, we can see a bit of Mil-Mel effect going on in here, but there's other interesting things that are being expressed here. For example, Shigeto Kawahara has a bit of research on how flight is expressed, how things that fly, there's a sound symbolic relationship with those, and Spritzy is pretty prototypical of that flyingness. Whereas Groudon is that larger, slower moving, more powerful, probably more dangerous. These are the associations that we kind of pick up through the name alone. So I took some of Shigeto's inspiration from his research and created AI that were trained on Pokemon names. And essentially, what these AI were doing was they were looking at whether the relationship, these are pre and post evolution. However, here I've just said small and big. So we can see that this is what's known as a confusion matrix that comes out of the type of AI we're talking about today, where the classification, if it's accurate, then that's in those green boxes. And we see here, this is a reasonably accurate AI. It's about a 66%, but not entirely accurate, right? Like because these are stochastic relationships again. But this is what the output of the AI looks like. It looks like each sample's fed into this confusion matrix. Small samples that are classified as small and big samples that are classified as big. These are accurate classifications compared to the inaccurate classifications. So for the study we're talking about today, we took 1,000 of the most common Japanese names and their gender distribution. This was taken from a website known as Forebears. Now, some names in Japanese are unisex, so a name like Chihiro, that can be a male name or a female name. However, we took this was from census data, and so we took the majority, like so for example, Chihiro is majority female. So in these models, we just said, okay, well, this is a female name. Phonemic transcription was based on a hiragana. And I had a couple of native speakers just quickly run through and check them to make sure that the algorithms were working properly. And each sample consists of a count of the number of times each phoneme occurs in a name. This can produce kind of a problematic data set if for traditional statistical hypothesis testing, because for most samples, they don't have those phonemes, so you end up with samples with many null values. However, these kind of samples work reasonably well in the AI algorithms we're talking about today. So there's a lot of positive benefits of using decision tree-based algorithms, such as the XGBoost, which is what we're dealing with today, mostly dealing with non-linearity and interaction, how they deal with missing data. They're more robust, they're more computationally intensive, which means that they use more of your computer's resources and they take longer to calculate than traditional tests. However, they're resistant to outliers, they're resistant to overfitting, and they handle large data sets really efficiently. The negatives, XGBoost algorithms, which is the algorithm we're talking about today, it's often described as a black box algorithm, which means that it's very difficult to interpret exactly how it's making decisions. There are risks of overfitting, particularly with a data set consisting of a lot of null values. They are computationally complex, which means that you will require a certain amount of time and computational resources in order to process them. They're not designed for inference. This is not entirely true. You do get p-values out of the models that I'm talking about today. However, yeah, it can kind of be difficult to get a grip of like whether something's statistically significant or not. And the ways that they do report statistical significance uh might be a little bit too forgiving, perhaps, but we can talk about that later. Now, the problem with regression in these models is that they don't really deal with collinearity very well. What we're dealing with is a very high dimensional data set, right? We're dealing with phonemes and phonemes that quite often we find sound symbolic relationships between diphones. So, for instance, like glimmer or glint, glisten, all of these words start with GL, that gl onset, and they kind of all have something to do with light or the shining of light. So, for example, in a regression analysis, you're not going to pick up those nuances. Um, Now, typically with this kind of data set, a, uh, you should be using Poisson regression because we're dealing with a count of the number of times each phoneme occurs in a word. Um, but you might also use linear regression if you're not familiar with Poisson regression. So the regression results for the Japanese names was that K and O were associated with femininity and the high front vowel was associated with masculinity. When I first analyzed this data set, I was doing so with a postgraduate student, and they suddenly, this looks like Japanese expresses gender opposite to every other language, right? So they were thinking, well, this is a really interesting thing. But I speak a bit of Japanese and I kind of had an idea as to what might be going on here. But instead of giving away the game, let's take a look at the decision trees themselves. So the way that these models are created is they're created by constructing many thousands of decision trees, and each decision tree is kind of consists of a random sampling of samples and the features. So the random sampling of samples is known as bootstrap aggregating, where what it'll do is it'll take a certain amount of samples out of the data set. The random subspace method is where we get our random sampling of features. And then, so each tree will consist of a random sampling of samples and features. And then the XGBoost algorithm, what it does is it kind of it builds upon the earlier trees, finding out what was like how were they accurate, were they inaccurate. It improves upon itself as it goes. And eventually you end up with a model that can classify samples. So this is an individual tree that I randomly took out of this model. So this is just one tree, but it gives us a kind of an interesting snapshot as to how things are going. We see here that the most important feature in this tree is the high front vowel. And this suggests that if a name has two or more high front vowels, then that's suggestive of masculine name, right? Now remember that high front vowel in other languages is typically associated with femininity. So this is kind of interesting, but it's interesting because it's specifically two or more, right? And remember, this is the most important decision in this tree. And what we see down here, these are our terminal nodes. These are kind of where the decisions are made. We can zoom out. We can take a look at this node section down here. We see that if there is a K in a name and an O in a name, these are both sounds that are associated with masculinity in other languages. We can see here that these are associated with femininity in Japanese. However, if there's a K and there's no O in a language, then in a name, then that's associated with masculinity. So there's something specifically about K and O going on here. Well, I hinted before that I speak a bit of Japanese, and I knew that these kanji often occur in female and male names, respectively. So we have ko, which is in many, many female names, such as Akiko. Um, ko, the meaning here of the logograph is feminine, is child, and it's just featured in many, many Japanese female names. And then ichi, as in daichi. Ichi is the logograph means number one, and it's often associated with being first. So you might be the number one strong, or the number one honest, or the number one whatever. Those typically occur in male names. So here we see the K and the O associated with masculinity in other languages. The regression tells us that it's masculine. However, those decision trees are teaching us, well, it's specific to K and O when they're together, right? And that's this. That's associated with this kanji. Um, so when we take into account that specific kanji, well, then Japanese behaves like other languages. Gender is expressed exactly the same way as other languages when we take into account these very specific logographs, which are very highly frequently occur in Japanese given names. So we see here, this is the model prior to taking into account those effects. We see here that we have a reasonably predictable, a reasonably accurate model here at about 77%. But remember that this is only based on the phonemes in the names, right? This algorithm hasn't learned that this name is female, this specific name is female, this specific name is male. This is simply the phonemes. So we're looking at a model that's trained only on the sound symbolism. So we kind of followed up that experiment. I wanted to see whether Japanese people would associate ko in foreign names as being feminine or masculine. So I basically created a bunch of foreign sounding names and presented them in katakana, which is how foreign words are presented in Japanese, and just had my participants assign Likert scales. And what we found is that any time that K and O appeared next to each other in those names, they got a very high score, which is associated with femininity. But in other cases where K and O were not put together, so not as co, well, then we didn't get such a high score for femininity. Yeah. So building these models, we reconstructed the machine learning algorithms using hiragana rather than phonemes, received much higher accuracy. I suppose that you could create models based on kanji rather than hiragana, which would presumably achieve much higher accuracy. However, there are 10,000 kanji characters, so that would be a data set that would be each decision tree would have to consist of many thousands of features, right? So we're kind of at the edge of the usefulness of the algorithm, right? Okay, so in Japanese, O was only considered feminine in the context of ko. Otherwise, Japanese follows the patterns of gender sound symbolism expressed in other languages. This is an interesting case study because it shows us that artificial intelligence can be used as an alternative to traditional statistical hypothesis tests and will uncover relationships that you may not have been expecting or that those traditional tests do not uncover. It's especially useful if your data is multidimensional, or when you expect some kind of independent variable interaction. All right, that's me. I hope you enjoyed my talk.
Okay, thank you very much. This is a very interesting talk. Very interesting. Uh, okay. In the chat box, David Wade said it to everyone. Interesting. I worked with Japanese women. Person is. So can you comment on that? Thank you.
Yes, certainly. So I mentioned the name Akiko. So typically what happens with a Japanese given name is you have two kanji characters. In the case of Akiko, Aki is autumn and ko is child. So that just translates to child of autumn. Um, So that's a very common combination. Keiko, there's a couple of different possibilities for I can't give the translation here because there's a couple of different possibilities for the kanji that can take the K position here. But I would almost guarantee that David Wade's colleague had that ko kanji in her name. It's very, very common in female given names in Japan.
Yeah, thank you. Japanese is very closely related to Chinese because it was said to from China a very long time ago, right?
Yes.
And Chinese has inherited a lot of Chinese characters to Japanese. However, in Chinese naming patterns, Chinese names are often associated with uh, the sexual connotation of the letters are not are much closely related to the phonetics. And for example, Li, uh, Lily, okay, the translation of Lily has a Chinese name of be related to a female name. However, other names are not necessarily this, okay? You know, Jun means army in Chinese. Okay, it has a strong connection with masculinity, and also Chinese names. Some Chinese names are related to the cultural customs or cultural traditions. They will give some strong names or masculine names to boys and the feminine names or names to girls, right? So, do you have any comments on this phenomenon?
Yeah, certainly. So what my experience with Japanese shows is that in Japanese, we still find those universal sound symbolic relationships. It's just that there's this specific instance of this specific kanji, which does come from Chinese originally, like in the 4th century, it was imported to Japan. And that's what is kind of influencing or the data set, right? It's when you use those traditional tests, it suggests that Japanese, well, it behaves in an opposite manner to every other language. But that's not the truth. The truth of the matter is that there's this one specific factor that's influencing it to make it look like a completely different thing. And were I to let, so this was uncovered originally by a postgrad student of mine, were I to let him off the leash and just go and publish the data, well, it wouldn't be the truth, right? Like he would be saying, well, Japanese expresses gender differently to every other language. Well, that's not really the truth. The truth is that we have this one specific thing. And without the machine learning algorithms, it would have been very difficult to prove that mathematically.
Okay, thank you very much. I think John May Kim has a question. Okay, please.
Yes.
Yeah.
It is very interesting talk, and thank you very much for your presentation. And I would like to comment about ko, that specific kanji. Now, well, in Korean name, we had soup, a specific kanji used to be only female name, soup. And then now it's almost disappeared. It derived from Chinese character, but these days people don't use that K sound anymore, and that specific kanji is being disappeared. Somehow the historical trends get influenced by this kind of Western influence or more of universal trend, and by having the disappearing Chinese specific kanji. And I would like to just add a comment to your very interesting talk about ko.
Thank you so much. Yes. Unfortunately, I'm not very familiar with Korean. I do have a colleague who's working on names at the moment, but I'm not so familiar, and I'm not entirely sure that you would attribute the decline of that specific kanji to Western influence. It might just be that Korean is evolving like all languages always do. So it could just be a natural formation.
Yes, I agree. It's evolving. Thank you.
Yes, you're welcome. There was another question.
Yes, Haruku, please.
So I'm trying to de-video myself. Okay, so thank you so much for very interesting presentation, and I was inspired by the previous person. And if you place this in a historical context, and I am an old English philologist, so I'm no specialist in your field, but the name ending ko is more like an early Showa invention. And if you go back to the Meiji period, that's not a common name. And Chiyo was a typical, for example, woman's name. And they now avoid the co-names, and Saki is my niece's name, and so on. So I was wondering, the very fact that you pointed out that, aside from the, suffix or whatever, ko, the rest is in line with the rest of the world. Is it possible that that's a Western influence, because the Japanese, as well as many other non-European people, are familiar with Western names, and sometimes names they come up with are very Western nowadays. So this is the overlayer, historical overlayer, and that's beyond your really fascinating research, but just wanted to throw some new element for someone's future research. Thank you so very much.
You're most welcome. I don't have any evidence for what you're suggesting. I haven't observed any evidence. I'm not sure that, I don't think that this specific case is due to any non-Japanese influence, but I'm sure that somebody could certainly be looking at it in the future.
Yeah, thank you very much, Alexander. Thank you all the participants